Good morning, ladies and gentlemen. Welcome to this session on recent results, where people are asked to submit papers on work that is still in progress or just completed. We've got 4 sessions this morning, one of which is coming in via video conference. So what I'd like to do is do all the presentations and then we'll take questions at the end. Our first speaker is Wojtek Nawrot from PSNC, and he's going to talk about alternative last mile connections with the use of cheap wireless systems. So I'll pass over to Wojtek.
I'd like to welcome everybody. My name is Wojtek Nawrot, and I'll present the topic alternative last mile connections with the use of cheap wireless systems operating in 3 frequency bands. It was prepared with the cooperation of 2 friends of mine, Wojtek Śronek and Krzysztof Turza, and I'd like to present the goals. The goal is an easy access to remote sites without the need to develop an expensive transmission infrastructure, such as optical fibers. Use of cheap wireless systems operating both in 2.4 GHz ISM band and 5 GHz Hyperlan free frequency band, and provide internet access to schools, libraries, and other low-budget institutions. A set of tests had to be performed to check whether wireless systems enable reliable transmission at high data rates in last-mile connectivity scenarios, both in urban and rural areas. The presentation includes selected throughput results obtained with the use of different sort of wireless equipment and different device settings. Also, problems connected with power limitation, installation, and maintenance will be introduced. Some advantages and disadvantages of specific solution will be presented, and optimum wireless solution selection for last mile connections will be shown. Okay, wireless equipment overview. We're provided some sort of wireless equipment, some sort of cheap wireless equipment from D-Link, Linksys, US Robotics, Senao, and from Proxim. Also, some cheap 2.4 GHz antennas were provided, 2 directional antennas from Interline, a Yagi antenna, parabolic antenna, and 1 omnidirectional antenna. And we also were provided a proprietary solution from Proxim Tsunami MP11A, and a panel antenna. Okay. Now let's consider optimum 2.4 GHz antenna selection. The testbed for antenna selection consisted of 2 notebooks, 2 access points, and 2 different antenna types. The tests for antenna selection were performed in urban area, the city of Poznań, at distance 2 kilometers. Line of sight was provided, and free Fresnel zone was also provided. We used 2 D-Link access points, 2 short 2-meter antenna feed cables, and 2 PCs. The software used: Network Stumbler for wireless network detection, Wavemon for SNR measurements and for antenna alignment, and Hyper for throughput measurements. We obtained some interesting results. The best performance was obtained with the use of 2 parabolic antennas with gains of 27 dBi. As you can see, the bigger total antenna gain, the better throughput and the SNR. The most effective pair of 2 parabolic antennas was used in the test of other access points. And now I'm going to tell you the dependence of range of wireless network. The range of wireless network depends on many factors. For example, the transmit power and receive sensitivity of wireless devices, gain of antennas, loss of antenna feed cables, pigtails, adapters, and other accessories. And it also depends on free space loss, the distance between antennas. It depends also on influence of obstacles, for example, trees, buildings, walls, etc. And also very important is the influence of weather conditions. For example, snow, rain, and even wind that can move the antennas. What is unpredictable is interface from other wireless networks and devices. Okay, now I would like to present a theoretical model of point-to-point 2.4 GHz wireless link. As we can see, the received signal level can be obtained with the use of the formula. I will not explain all the symbols in the formula, but I would like to show that with the use of 17 dBms transmit power and short antenna feed cables with 3 decibels of loss and 27 dBi antennas, the received signal level is minus 54 dBms. That allows for 54 megabits transmission connection speed. As we can see in yellow box, with the use of combination of transmit parameters, the allowable EIRP was exceeded. In Europe, the permissible EIRP is 20 dBms, 100 milliwatts, and using the parabolic antennas and maximum transmit power of the access point, we obtained 41 dBms or 12.5 watts. That's 120 times more than it should be. Okay, if we wanted to provide 20 dBms of EIRP, we should use the transmit power of 3 dBms, longer antenna feed cables, for example, with 10 decibels attenuation, and the same antenna, parabolic antenna. But the received signal level in this case would be minus 82 dBms, what can provide the transmission speed of only 12 megabits per second. So the EIRP limitation is a big problem. But for wireless systems testing purposes, no EIRP limitations have been followed. Now I'm going to show testbed for 2.4 GHz wireless systems and the testing procedure. The tests were performed during the summer 2004, but now we are still testing new systems operating in 5 GHz frequency band. All the 2.4 GHz access points were tested in point-to-point topology using a pair of 27 dBi parabolic antennas. 5 GHz tsunami system was tested in point-to-point topology also, as well with the use of power antennas provided by proxy. The measurements were carried out both in urban and rural areas with the use at distances 2 and 3 kilometers respectively. The equipment was placed on the roofs of buildings so that the line of sight and free fresnel zone were provided. 2-meter antenna feed cables were used to limit signal loss. There was the following testing procedure. TCP and UDP throughput were measured, jitter and packet loss as well. It was done with the use of iPerf and two PCs. Hyperv tests were performed with maximum transmit power for different TX rates at specific optimum channel. Now I'm going to show the selected results because in the thesis I had a lot of graphs. I chose the most interesting ones. As we can see, there is a comparison of results both for urban area and rural area at distances 3 and 2 kilometers respectively for both 2.4 gigahertz systems and 5 gigahertz systems. As we can see, the throughput obtained in urban area was about 5.5 megabits per second, but in rural area it was 17. It's 3 times better than in urban area. The best throughput result in urban area was obtained with the use of 22 megabits transmit rate, but in rural area the best results were obtained with the use of automatic mode. As we can see on the right charts, both for urban area and rural area, the differences between obtained results are not very big. And some conclusions. 2.4 gigahertz wireless link performance depends mainly on interference rather than on distance. Because the distance in rural area was 1 kilometer longer than in urban area, we obtained better throughput results. Such a rule doesn't exist in 5 gigahertz frequency band because both in rural and urban areas the results were very similar. For high performance of 2.4 gigahertz transmission, an appropriate channel must be selected and changed every time when the network performance falls down. 5 gigahertz systems provide automatic channel selection, what makes them better than 2.4 gigahertz system. In urban area with numerous wireless networks sharing 2.4 gigahertz frequency band, TX rate of 22 megabits per second provides the best performance. This is the mode 802.11b+. In rural area with low 2.4 gigahertz frequency band utilization, TX rates of 36 megabits and greater provide the best throughput results, as I told during description of previous slide. The best 2.4 gigahertz wireless link performance was obtained with the use of D-Link access point and US robotics access point in 2.4 gigahertz frequency band. Measured throughput differed for downlink and uplink connections despite point-to-point topology and equal transmit power of wireless devices. It was probably because one of parabolic antenna could have received more noise than another one. For 2.5 gigahertz transmission, ping response times differed a lot, while in 5 gigahertz frequency bands they were short and constant. That's very important for time-sensitive applications. Okay, now let's compare 5 gigahertz solution and 2.4 gigahertz solution. 5 gigahertz wireless systems operate in the 5.4 to 5.47 gigahertz hyperLAN band with maximum EIRP of 1 watt. But 2.4 gigahertz wireless systems operate in ISM band that allow merely for 0.1 watt. What's very important limitation. 5 gigahertz systems provide dynamic frequency selection and transmit power control. 2.4 gigahertz systems require manual frequency and transmit power selection for high performance and compliant with regulations. 5 GHz systems provide non-overlapping frequency channel that prevent inter-channel interference. In 2.4 GHz systems, overlapping channel deployment schema causes inter-channel interference, leading to network performance fall. In 5 GHz, with the use of 5 GHz system, antenna alignment is simple thanks to built-in antenna alignment tool. You can simply observe the signal strength at this appropriate software delivered with, for example, Proxim Tsunami. But using 2.4 GHz wireless systems, parabolic antenna alignment is time-consuming, complicated, and requires a huge precision and additional hardware software tools. Many 5 GHz solutions provide non-line-of-sight connectivity. We turned a panel antenna from Proxim Tsunami about 90 degrees left, and there was still connectivity. But for high performance, the line of sight and free frame result should be provided when using 2.4 GHz system. 5 GHz system provide improved security, but 2.4 GHz system provide imperfect web-based security mechanism. It's not very difficult to break into wireless 2.4 GHz network with 64 bits web key. There are majority of models and functions when using 5 GHz wireless systems. For example, bridging, routing, frame and packet filtering, quality of service, VLANs, and spanning tree protocol. But 2.4 GHz systems only provide basic functionality. They can operate as access points, bridges, AP clients, or repeaters. The only disadvantage of 5 GHz wireless systems is relatively high price. The complete point-to-point link can be bought from 2,000 to 3,000 euros, but complete 2.4 gigahertz point-to-point link can be completed from 500 euros, and it's the advantage of 2.4 gigahertz solutions. Okay, now let's show optimal solution selection for last mile alternative connections. 2.4 gigahertz wireless systems are cheap but problematic in installation and maintenance. They require administrative supervision due to channel changes. Most wireless devices are designed for indoor use. They have very narrow operating temperatures, and they don't have protective waterproof cases. So they should be placed in buildings, or they should be put into a plastic box that protects them from the influence of water and freeze, etc. Due to EIRP limitations in the ISM band, Wi-Fi systems are suitable for in-building applications, and they can supply short wireless links between buildings. Common Wi-Fi popularity causes continuous increase in the number of new wireless networks, what makes the performance of existing networks lower and lower. 5 GHz wireless systems are relatively expensive but simple in installation and maintenance. They are light. They can be simply attached to the antennas, can be simply attached to the wall or to the mast. So during the installation, we didn't have any problems with it. No frequent administrative supervision is necessary thanks to dynamic channel selection and other advanced options. ERP of 1 watt in 5.4 to 5.47 GHz hyperLAN band allows building long-distance wireless links, both in point-to-point and point-to-point and point-to-multi-point topologies. Most systems are designed for outdoor use. Numerous devices are integrated with a panel antenna, panel directional antenna, and an increasing number of wireless systems for hyperLAN band makes them cheaper and suggests them as the way to provide low-budget institutions with broadband internet access. About a year ago, only Proxim Tsunami was available on the market as a system that works in 5.4 GHz frequency bands. During last year, new solutions appeared on the market. For example, Libra 5400 from Wylan, Motorola Canopy, some Triangle solutions, and some solutions from RadioNet. Now we are delivered these systems and we are testing them. Okay, that's everything. The questions can be asked at the end of the session. Thank you very much. Good. Okay, thank you.
Good morning, Comrade Zacconi from AWT.be. So on your different tests, I saw that you used parabolic antennas in order to cover that last mile situations. In many countries, it's forbidden, in fact, to use parabola antennas to make point-to-point links because there are government laws and so on. So do you think that in order to have a good quality for last mile connectivity, parabola antennas will be required, or Yagi antennas might be sufficient in order to cover the needs? And have you tested with
I
Yagi
think
antennas?
that parabolic antennas can be replaced by others antenna configuration. It's important to provide the received signal level at a specific signal level, but we obtained the best results with the use of parabolic antennas. We exceeded the available ERP, but for testing purposes, we didn't follow the restrictions, and we're aware of the thing we've done. But you have to, the power budget should be okay, and you can replace the antennas, for example, with antennas with smaller gain, but I think that the performance will be lower.
Just second fast question. Do you think that in the future we might use point-to-point wireless link as, let's say, main connectivity, or we should continue to use them as a backup connectivity for the network?
We're trying to use parabolic antennas and Wi-Fi systems as primary solution for low-budget institutions because they are unable to build, for example, optical fibers. So, if there is no another way to provide the connectivity, it must be the only way. But with the use rather of 5 GHz wireless systems, I think.
Thank you.
Thank you.
Thank you very much for that. I'd like to welcome Filippo to the Terrena conference, who's sitting in the University of Milan. Hello, Filippo.
Hi, can you hear me?
Yes, we can. Filippo is going to talk to us about wireless connected tablet PC and GPS for on-campus micromobility research at the University of Milan. So I'll hand straight over to Filippo.
Can you hear me well?
Can you hear him at the back? Yes, they can hear you.
Can you see me properly?
You're a bit fuzzy, but I think that'll be okay.
Okay, I go on with the presentation.
Please do.
So, first of all, thank you for inviting me at the Terrena conference. You will have to excuse me for some inaccuracy in my relation, since my presentation seems I'm not an information scientist from my background. Today I will present you an experimentation we did at the University of Milan Bicocca in last winter. It has to do with the use of network technologies for mapping the mobility inside the area of the campus. So probably you can put the second slide and give me a feedback about that. Can you see the second slide?
Yes, we can see the second slide.
Okay, thank you. I want to spend a couple of words about the physical context in which we made this experimentation. It's a multifunctional area in the northern part of Milan, in which we have a university, the University of Milan Bicocca, that is dislocated in non-continuous buildings. We have, okay, now I think I can see my slides. Oh, no, I meant the previous one.
I think he wants the next one.
No, before. If you can go back with the slides, please. The second slide. Second slide.
Is that the one that starts technical devices?
No, physical context. Physical context.
Keep going. Keep going.
Before that.
Don't think we've got that one, Filippo.
I'm talking about the second one.
Go back to the second one.
First and the second.
This is the second one we have.
You don't have the physical context one.
No.
Okay.
These are the ones we've downloaded 2 minutes ago.
I guess I can talk about the physical context anyway. So I was saying that there's a university, there are a few huge residential buildings, and there are 2 corporation headquarters in this area and a big theater. So it's a kind of complex area to be studied in terms of mobility, and we study mobility in order also to take better decisions on where to allocate brand new network technologies on the campus. So I'm seeing the technical details slide, so I guess I can switch to that. So I'm talking about an experimentation that involved 17 students in the specialistic degree of sociology that were asked to, let's say, track the mobility of people around the campus through tablet PC. They used the TravelMate C112 with the GPS receiver to locate the user, and they were asked to stop pedestrians and to ask them the permission to follow them. The track registered in the system. So in the service side, we used ArcGIS for processing all the data, and on the client side, the user could visualize ArcPad and a computer-aided personal interviewing for collecting some qualitative data on the pedestrians. So they ask the pedestrians to give them some data about age, kind of work, and the purpose of the trip. So they follow the people during the trip inside the campus, outdoors, and then when the trip was ended, they memorized the new spot in the system. So I guess we can skip to the next one. Yeah, the next one may be the previous one. So there were 9 sections of data collection during 3 contiguous days from 4 starting points. One was the train station, that is an access point of the Bicocca area. The other 2 are the main buildings, main university building, and the 4th point is the area where all the university restaurants are located. So another thing to be said is that students were asked to collect the data during 3 different time bands during the day, so morning, noon, and afternoon, in order to confront the mobility patterns also throughout the day. So once the data were collected on the field, they were aggregated in the lab through the artists, and the students were asked later on to provide to make some query to the system to generate some maps for different evaluation. Later on, I will be clearer on that. So next one, we can skip to the next one. So here you have a screenshot of the client application. So what student visualized in their tablet PC. There's ArcPad and there's the personal interviewing systems. These 2 systems then would have to be matched separately by another researcher. In the latest version of ArcGIS, you can visualize from the lab directly the field and get the data instantaneously. Going on, I can show you some output we got from this kind of work. So this is a map of made by students that shows the students' mobility, because it was not just a matter of collecting students' mobility, but also to collect retired people mobility and workers' mobility, depending on their speed. So yellow to red, slow to fast, and these kind of data are important since we wanted to understand which were the better locations for example, information kiosk to be located, or which kind of data, information, we could have provided to users located in a certain area of the campus better to users located in another area of the campus. So if we skip to the following one, yes, this one with the previous one, I guess. No, I mean they are now backwards or forwards, I guess at this point. Okay. Okay. Here you can see 2 type of lines that again are about the speed of a mobility, and then you can visualize some different colored spots. The spots are referring to people in movement in different time bands of the day. So we can see an aggregation of red spots near the main university buildings in the noon, around noon, and a different kind of mobility during the two other segments of the day, in particular a more transversal mobility. So what can we infer from this? Next one, please. Main operational results. Yeah, probably I can spend a couple of words about the operational results. That probably, since you are all much more competent on this, it's not so interesting. Better than me, it's not so interesting for you. But so the lessons we have learned is that the use of wireless technology to collect this kind of data provides an easy data transfer from mobile devices to the server, a good control on the quality of data, an easy access to the data once the collection has been done, and an efficient process and management of dataset implementation. I'm referring to the matching of georeferential data with the collected questionnaires. Next one. So, as for scientific results, we can talk about two different kinds of mobility that we have found out inside the area. The first one is a more structured one, and the second one is more, how can I say, disorganized, the structure. So the most structured one, that is the more finalized and objective-oriented one, is happening in the peripheral areas of the campus, mostly from commuters that, whose approach is very functional to the university. And yeah, we found out that they move pretty fast. And this kind of movement can be recorded more in the second half of the day. On the opposite side, we have a completely different category in terms of mobility that is made by mostly by residents, so people who are coming from the neighborhoods or from inside Milan, that move around the campus in a different way. They move slower. They move mostly in the central areas, so it is kind of obvious that they don't use too much the train, so they don't go to this kind of access point, access gate, sorry. And they move around mostly during the first half of the day. So, if you skip to the next one, what are the consequences? What are the lessons? What are we going to use data for? So, first of all, we would like to enter the implementation of location-based services on handheld devices like cell phones that everyone in the campus have, to provide certain kind of services like daily news or latest news, like okay, this lesson was cancelled. And in order to do that, we are launching a new research lab called Nomadis, which will soon sign some partnership with the main telecoms operators here in Italy. And the main problem as for this is the precision with which the telecom operators can locate users. So we still have to figure out the order of precision, also depending on where the cell towers are located in the nearby, to figure out which kind of precision we can provide to the user of the campus. And again, knowing that some areas are populated by people that move faster than others, and people that have some features different than others, we can provide more personalized services to each of them or each of these categories. The second interesting application for this kind of study is the allocation of information kiosk. That is another intention we have, still unclear where we are going to implement it and when, but it's we are planning to do that. So probably the information kiosk will be allocated mainly in the central areas, since in the peripheral areas people tend to move faster and want to lose their time in accessing an information kiosk. Last but not least is this study was an opportunity to be more informed where to extend the Wi-Fi access in the outdoors. At the moment, the Wi-Fi access is mainly located in the indoor and only in certain areas of the campus. So before investing into this, we want to be sure that the area that which we were going to cover were enough populated and moreover were populated by people that had at that time to spend and at certain patterns of mobility. So yes, these were mainly the results, and yeah, I'm afraid I didn't show you. I were not able to show you some maps and some images that gave the idea about what happened into the field, but it's pretty simple. And okay, I'm here for any question.
Thank you, Filippo. I think as the sound's a bit iffy, maybe we'll take questions now for Filippo. Any questions? No? Can I say thank you very much for joining us, Filippo, and good luck with your research. Thank you very much.
Thank you.
I'm pleased to welcome our next speaker, who is Stig Venas. He's currently working at the University of Southampton in the UK, and he's going to talk to us about IPv6 renumbering. Stig.
Yeah, thanks. Your presentation. Yeah, it should be there. Yeah. This one? Yeah. Oops. Yeah, okay, thanks. So I'm going to talk about IPv6 renumbering. The first question you might have is, what is renumbering? It's just a technical term for changing IP addresses. So we're going to talk about how to change IP addresses. That doesn't sound very interesting, but well. So what we'll look at is, well, first of all, why is this special for IPv6? Is it more complicated, easier to change addresses than IPv6? Do you need to do it more often than IPv4, or what? Also looking at sort of what people have done about this before, what tools there are for doing these kind of changes. Looking at experiments we can run to see how easy it is to change addresses and so on. And what happens with management tools when you do this. Recommendations for administrators, implementers, and so on. And future things that can be looked at. So why is this more interesting for IPv6? In IPv4, a large company usually have their own addresses, their own IPv4 addresses, and if they change their provider, they keep their addresses. Well, for IPv6, you always get IP addresses from your provider, which means that if you change providers, you also have to change addresses. So this is sort of the main problem. The reason for this is that Well, in IPv4, the routing table is getting very large, and the main reason for that is that people keep their addresses when moving around, changing providers and so on. If people always get addresses from their providers, then you can aggregate much more, so you don't need more routes than you have providers, more or less. There's been some proposals for how one could have provider-independent addresses in IPv6, but none of them has been accepted, and people are a bit scared about this size of routing tables. Another thing is that in IPv4 you can use NAT if you want. Then you have private addresses inside your network, and if you change your provider and which addresses you have sort of outside of your network, it doesn't affect which address you use on the inside. But for IPv6 there is no NAT, and we don't really want it. So we want to see how we can accomplish these things without the help of NAT. So some people have been thinking that we could make IPv6 so that you can renumber and change addresses more or less just by a click of a button. But it's not really that simple, as I'm sure you understand. One thing is which IP address a host has, but there's lots of addresses in hosts or in config files and applications and so on. It's not so easy. So we're trying to look at different renumbering scenarios, looking at what issues might come up, looking at which applications have addresses embedded in config files and so on. And finally, we want to come up with some recommendations from this. So there's been some work in the IETF on this before IPv6. It started in 1997, and there's a few RFCs, but there's no work going on at the moment. There's a couple of drafts on IPv6 and renumbering out there, which I'll discuss later. There's a number of features for IPv6 that could help us with renumbering. Maybe the main one is stateless auto-configuration. With IPv6, you can have routers announcing which prefix you should have on a link on an Ethernet, the first part of the address. And then the hosts will generate the last part based on a MAC address, and you will have a complete address. And if you change the addresses on a link, you just announce the new prefix, and hosts will immediately also get a new address using that prefix. So this helps a lot, but there's more to it, as I said, than just the addresses on the hosts. Also with IPv6, it's very easy to have multiple addresses and have on a host, on an interface, and have multiple prefixes at the same time. This is very useful. There's also a couple of other things, like how to get a complete prefix from DHCP, or there's a router renumbering protocol standardized but not implemented as far as I know. Mobile IPv6 could maybe be of help in some ways, because mobile IPv6 allows you to send sort of binding updates saying, I got a new address, now please contact me on this address instead. So maybe you could sort of preserve ongoing sessions while you are changing the address on the host, but it's not clear how it could be done. Part of the problems with the router renumbering is that you need some PKI or something like that in place. So it's not so easy. So there's one internet draft from IETF about how to renumber without a flag day, which is quite interesting. So let's see. So the idea is with IPv6, it's possible to, as I said, have multiple addresses on the host, and you can use this to have a very smooth transition from one address to another. So basically, you would go through the 5 phases you see up there when you renumber. Initially, you have a stable situation with just one prefix. Then you can introduce a new one, and the host will have 2 prefixes at the same time. And then applications will use any one of them. But then you can say that the old one is deprecated, which means that it's still possible to use it, so ongoing sessions will work. But when an application creates a new session like TCP session or something, it will avoid using the old address. Then finally, when you hopefully have no more sessions using the old address anymore, you can then say it's not valid anymore, and you have a new stable situation with a new one. So it's sort of how to just do the change of address on an interface on a host is sort of taken care of. There's lots of other issues, and I've been trying to list those in the other internet draft, which you see at the bottom. So it's basically about all the other ways or places IP addresses show up and how to manage them. We have done some experiments, like some home network or small office, and it's reasonable, simple. It works pretty well. But you have to be careful about which order you change things and so on. Some of this might also be the case for enterprises, but we haven't looked that much at that yet. One key thing is to try to use not IP addresses but domain names or host names as much as possible, and use DNS for looking up addresses. And by carefully controlling which addresses you have in DNS, you can do things pretty smooth, but there are some issues. One thing, of course, is that you need to be able to access your name server all the time. If you change the address of your name server, you have to tell all other clients about the new address. I've seen some issues with management tools. I think there's more about that at another slide. Then you have, as I said, some applications have config files with IP addresses. One example is Apache, which has, if you use virtual hosts, different domains for different addresses and so on, you have to update that, for instance. Since you can do this change with having two addresses for a while before you disable or remove the old one and so on, you can cope pretty well with sort of short-lived applications or sessions like SSH. If you have an SSH login for 1 hour or something, it's not a problem if you change addresses during 24 hours or something like that. But you might have other applications that have a session that lasts for weeks, perhaps. We plan to test the DHCP 6 prefix delegation, but we haven't been able to do it yet, unfortunately. Part of the work we're doing is also, there's an organization called Join, which also is involved, and they've been running an IPv6 academic backbone in Germany, and they have renumbered their network from using the 6-bound addresses to official addresses, and got some experiences from that. There are a number of issues, but some of them are very particular, and I can't really explain all the details. But you really have to be very careful about which order you do the changes in your network. So you have to think very carefully about what you're doing, which steps you're making, and so on. One particular thing, perhaps some of you may have heard me talk about embedded RP on Tuesday, or was it Monday? I don't remember. But anyway, you have multicast group addresses with an embedded RP address. But that means that if your rendezvous point changes address, then you need to also use other multicast group addresses. We have seen some issues with management monitoring tools that don't detect that a router or a host has got new addresses. Another issue, but I think I got it on another slide, is that some tools might think this is really two separate hosts when it is one host with two addresses. It may be difficult to distinguish that. With IPv4, you often, I think, say that sort of identify the IP address with a host. But with many addresses for a single host, this isn't the case anymore for IPv6. That's here. So part of the issue is, during renumbering, you might have two active prefixes, and so one thing is the management tools, but you also have other things like access lists that need to accept perhaps both the old and the new prefixes or addresses. You have that's sort of access lists on routers, or there might be for applications like Apache saying who can access its web page and so on. And if you want to renumber gradually, doing part of your network at a time, then the one part you start changing the addresses at may need to have access to other parts of your network, so you need at least to update access lists and so on in the other parts to give them access. So there are things to think about before doing a renumbering. We're trying to look at different recommendations. So we'll have some examples. One thing is it's nice if providers can give customers a static IPv6 prefix. That means that while you stay with the same provider, you can keep the same address. But I heard some providers say that they may like to be able to change this sometimes if they restructure the network or move a customer from one routing port to another or something like that. The other thing is it's been suggested that sites should get a /48 prefix in IPv6. And if you can always get a /48 from your provider, it makes it much easier, because if you change providers and a new provider told you that, oh sorry, you can only get a /56 from us or something like that, then you may need to reorganize your network, because you can't have that many levels of subnets and that many levels of hierarchy and so on. If you keep the same length, then you can keep the structure, just change which addresses you have. There's also something called unique local addresses in IPv6. So that's almost like the private addresses in IPv4. So the idea is that you can use these addresses perhaps to have communications internally between the hosts and routers in your site. And that would mean that if you renumber, the internal communications can be unaffected, because you just change the global addresses. But I'm not sure if this is a good idea, though. There's lots of issues. Like you may need two-phase DNS with getting different addresses if you look up a name on the inside of your network and the outside. And addresses might leak out of your site, and it might be difficult for applications sometimes to know which addresses to use, especially if you have referrals between applications and so on. One important thing is to avoid IP addresses as much as possible. Use domain names instead, so that you look up which address to use at the moment you create a session, for instance. And also not cache DNS lookups for long times. Another interesting thing perhaps is in IPv6, as I said, you have this auto configuration where you can get an IPv6 address based on your MAC address. But if you have a server, you often want to manually set an address that doesn't change if you change your network adapter or something. So you typically, for instance, say a server is just, the last 64 bits is just column 10 or something like that. And one interesting thing could be that instead of having to manually set the entire address, you just manually say what the last 64 bits should be. So if you change the prefix, you keep this manually set last 64 bits. But today you typically set the entire address if you want a manual set address. Another thing is maybe to use symbolic names for prefixes. Imagine, for instance, if you have an access list, you could, instead of specifying the complete address, you again specify just the last 64 bits or something like that. And then if you get a new prefix, if the first 64 bits change, you can still use the same access list. So you can say, like, accept any address that starts with the same as my address or something like that, and ends with something specific. Yeah, so some conclusions. There's going to be more renumbering in IPv6 than it is for IPv4, I think, because of this change of providers requires a new address. And there are some tools and mechanisms for how it can be done easier or simpler with IPv6, but there's lots of issues to look at. And we plan to continue looking at these problems and come up with more recommendations and so on. Yeah, so hopefully there are ways of making it easier, but yeah, it's not trivial to change addresses. So, yeah, that's it.
Thank you very much, Stig. What I'd like to do is take questions at the end after Eduardo's spoken and get all the three speakers that are here back at the front. So, thank you very much to Stig.
Yep.
I'd like to welcome now our next and final speaker, who's Eduardo Jacob. He's from the University of the Basque Country, and he's going to talk about very low-cost wireless IPv6 access routers. So I'll pass over to Eduardo.
Thank you. Well, good morning. My name is Eduardo Jacob. I'm going to present this agenda for the presentation. There was a motivation because we were clear bit of our research group on IPv6. We have done some work that I will not describe here. But we had another set of motivations. We had already had experiences with IPv6 in our research lab, and that experience had to be done without disturbing the corporate connectivity and services. That's because in our university, as in many others, the network is run by other people, and at this moment there was not a clear bit from then on IPv6, and we had connectivity from a European project as collaborators. So we had to make these experiences. We did them. They are reflected in a paper we write. But we also were willing to play with IPv6 in another two additional scenarios. One of them was to bring IPv6 connectivity out of our lab. So we are not allowed to put cables in our university installation, so it was not easy to go from our lab to our working sites. Also, we had another idea that was to play at home with broadband ADSL or cable modem connections in order to try it. In this research solution, we found that the wireless router appeared spontaneously, and it could be very interesting to us. At the point when we began this work, there were no integrated IPv6 routers, and we developed this work also for providing us for an infrastructure to support other works. We decided to choose the hardware with some requirements. One of them is that it had to be economical because it should be installed in exposed zones, for example, removable ceilings, public corridors, where they can really be stolen, because it's very easy to take something. We also needed several units to get the decent coverage. Another requirement was the need for quiet operation. It's normally interesting in the lab or in public corridors, but we found that in the home it's a requirement very interesting because nobody wants to have a noisy thing in his room. Another requirement was the footprint. We think that a small footprint is needed for installing it in ceilings or places like that. We had several choices for choosing our hardware. One was the dual recycled PC. There are many PCs laying around in our labs, but there are advantages. For example, the cost is very good because it's there. You don't need normally anything more. This is also relative because if you are now going to buy a memory piece for old machines, it sometimes costs you much more than the new one. But there are problems. One of them is that every PC is different from the other one. They are normally very big, they are noisy, and normally need a Wi-Fi board. That in many cases is difficult because all PCs normally have some stuff like ISA boards that are normally not available for Wi-Fi board, and there are normally also no USB connectors. We already tried, the first one we didn't try, we didn't bother try. We did try single board computers in PC104 or Mini ITX. These are very, very good pieces of hardware. They are very small, they are very silent. You can get 1 GHz CPUs without any kind of fan, so without any kind of noise. You get them with NI 386 architecture, what makes it very easy to work with Linux or those kinds of stuff. And the downside it is that there are more or less they cost much money. Normally, if you are thinking related to other kind of hardware. Many times also you need a specific Wi-Fi board that many times cannot be put down laying. You have to put it upside. There are some problems. You can also have SBCs with a Wi-Fi board incorporated, but it is somewhat expensive. And the third solution was to use low-cost commercial off-the-shelf Wi-Fi routers. That's the approach we have finally selected, as you will surely agree. On the plus side, their cost is very fine. They are very small. They are silent. They don't have any fans. They are also operated by a low power continuous current power source. And they have other facilities, as for example, integrated access point or switches. And they are based also on GPL operating systems, normally. On the disadvantages, we can think of mainly in one. It's that the architectures are not based on i386. So normally you will need a cross-compilation approach. The hardware we selected is the Router Link 6, the WRT54G. At this moment, it's about 70 euros, and you get all the things you can write just there. But most importantly, you get wireless BG on board. You get a 4-switch port, and most importantly, it's programmed with GPL code. Although there are some modules that are closed source or binary modules. We had already done this kind of work with another wireless router, the USR 2450. This hardware is very different from the other one. You can just see that, for example, in the old one, the wireless board was a plain PCMCI board that was just plugged in. That was also the way to program it. It was somewhat cumbersome to program it, and the problem was that it was a very low capacity CPU. So if you had to do something like VPNs, those kind of things, you had really problems because there was not much power. There was also the problem of not having a switch, and also the problem of having a very small memory. Well, the software requirements we choose was this one. We needed to access to the configuration through IPv6 or IPv4 from a client command line interface with SSH of Telnet and www. We also needed to be able to fix IPv6 parameters from both kind of interfaces, and we would like to offer several tunneling mechanisms, although only several of them would be available on the www interface. There were also specific IPv6 requirements, like, for example, the root advertisement. Well, the integration with IPv6 was done through the concept of IPv6 clouds. We think that normally the the equipment that would use this kind of routers would be dual stack nodes, normally wireless, although it could be also wired because we had really switch in the equipment, and we were using stellate auto configuration. The connection to IPv6 would be native through an IPv6 link, or through an IPv6 backbone, as for example in our labo. That was a clear, or in the home use. It must be said that there are problems with traversing NATs in small offices and house, and in some small enterprises because of the particularities of NAT. We have also the problem with DNS that's only related to IPv4 right now. This router has had many firmware available. Some of them were free, some of them were paying. And we chose Satori 4 of SBAsoft. It was very proven and had many additional features over the base version. What's the difference between this platform and the normal PC platform we are used to work with? First, there is no massive storage system. There is only a very small non-volatile RAM area that is accessible to store configuration data. That means that we cannot think about file system in the more generic sense. There is also not much place for a full-fledged distribution as we can think of it. The development system is obviously not on the platform because of not having massive storage requirement, and that also gives the necessity of cross-compilation. And the third and perhaps biggest difference is that we have a different CPU. That means that if we want to add some software, we really have to choose, if possible, sources that support the CPU natively, because if not, you have really much more work. The development environment is a normal one, because compilation development. You develop on a host machine, you create an image, and after that, you flash the image on the target. This is somewhat slow because you have, for doing every test, you have to really to generate an image, to send it to the router and flashing it. And if you do things wrong, you have to do a hardware reset. But when I say hard, it's really hard because you have to short pins on the main board of the router. You have to do some complicated things that are somewhat stressing. The good side is that the toolchain needed for this is available from Linksys. So it's that point of view, although there is some work to put all the things for working, it's somewhat polished. We think in the platform, in software platform, we can think of three groups of modules. There is a group of non-modified modules where we can think about wireless LAN, the authentication and the bridging that don't need any modification. We have some modified modules that are the shell applications. We're speaking, for example, for applications that need to take in account IPv6 address. We have to tweak also the kernel support. It's normally nothing more than activating it. We have to give IP tables also an IPv6 capacity. And we have to think about routing and access. Normally, most of this functionality are given by a client-server interface. I think I will not explain this stuff because it's almost, I think it's all explained in the slides. Normally, we have to do is activating the dual stacks in everything. We had to do several modifications in several daemons at the socket level call. In those kind of platforms, the more used commands are the CPLS or the commands of the shell are not offered as independent program, but as a program named BusyBox that incorporates of all of them. We had to upgrade the BusyBox and activate IPv6. We had to configure the kernel, and we modified IPv tables to properly support IPv6. We upgraded Zebra for giving IPv6 support. We installed and compiled RADVD. This included compiling Flex with MIPSL support for getting a library. We installed the TSPC client, for example, for getting TCP tunnels. And we modified the configuration screens on the WW access. Curiously, this many work had to be done because of the way it is coded. One important point also of work was the modification for storing and reading configuration data in the non-volatile RAM from binaries and from scripts. Because I have said before, there is not a properly file system. You have to read and store information in a special way. The modules we did not modify was the related to wireless LAN, because there are closed source modules for from Broadcom, and we are actually working on a proxy-based solution. I mean, we are going to implement a proxy that will listen on the IPv4 address and transform it to IPv6. Bridging was also non-modified. This is real screenshots. We can see that we can access from IPv6. We choose to implement on the web side TSPC and 624, also with configuration of 624. And the results at this moment is that it works. We don't have deployed it because of problems with our formatics department, but we think we will be able to use it because that's the way where you really see problems. We can see that it works fine with IPv6. Stateless configuration works okay, routing works okay, and tunneling works okay. If we think about the impact of adding all this IPv6 functionality to the image, we are speaking that we get 3.04 megabyte image size instead of 2.6. So it's roughly about 400 kilobytes of binary code. We had, I have left something in Spanish. We had several scenarios compared. We tried in the wireless scenario. When we speak about modified router working in IPv4, it's the Satori modified working in IPv4. I mean, the double stack router working only in IPv4 and IPv6. We also made a comparison with the modified router working in IPv6 and the original working in IPv4. When I mean original, also I mean the original Satori for sources. Well, we did all this kind of scenarios. We used several file sizes and several number of clients running at once. We did for every of these scenarios four runs, and we did median value. We got many tables. I will not present them. And the conclusions we had, we started about it. It was first that it was possible to do it. Another one was that in a wireless scenario, perhaps due to the low speed, there are no big difference in any case. A conclusion that was very interesting is that adding dual stack didn't decrement IPv4 performance when compared with a pure IPv6 stack. That's one of the main concerns of people of embedded systems, when you speak about them, to put in dual stack, is that they said, well, perhaps I lower my performance numbers if I add the dual stack. we can demonstrate that this, at least in this hardware, does not happen. And the big surprise came that the router had better performance in IPv6 than in IPv4 in the wireless scenario, in the wired scenario. Perhaps it's we really know that it's perhaps a particular case because there is no header processing involved, so this can eliminate much of the problems that you can get in core routers, perhaps. But in this kind of routers, we found that, at least in this case, this was what we found. The corollary, that the very good conclusions we find for us, is that adding dual stack to general use in embedded system doesn't hinder performance when compared to IPv4 only systems. It seems that some of the promises of IPv6 could be true, at least in some environments. The future work, we would like to dive into the numbers and find the origin of the difference of performance to try to narrow what is the cause. We would like to integrate the IPv6, that's almost done. We would like to integrate 802.1x radius with IPv6 and work perhaps on a proxy DNS solution. Well, if you have any questions, I would be glad to answer. Thank you.
Thank you very much, Eduardo. Have we got any questions for any of our three speakers that are still here? We've got Stig, Wojtek and Eduardo. There's one down, right. One at the top, one there, then one down here, and then one down here.
A slightly selfish question, actually. I have a Netgear box similar to this at home. You don't know if there's any work similar to what you just described for the Netgear box. I've forgotten the actual model number, but do I have to do what you've just done myself, or?
Well, I really, I think I have understood the question. I have understood. I really don't know if this work in a Netgear box. I really don't know.
I know it's got an open. It's got a GPL operating system on it.
Yes, I think the concept is wholly applicable because the problems are just there. The more new the distribution is, the more chances you have that IPv6 is really ready. I have even read that latest distribution from Satori that at this time of paying distributions have IPv6 support. So that means that in a year or two you will have those distribution in the public domain with sources and you will have it. But I cannot give more information.
Right, there was another question down here, and then there was one at the front. We've got one up there as well.
I have first a question for Eduardo. Does your firmware is, let's say, freely available for testing for other enterprises, or it's just still up to now, just related to your work? And
it's still a work in progress. We don't feel that it is really it can be made available because at this point it's not polished at all. We are working on it, and we would like to publish it, but we have some fear about having to answer questions and giving support to it. It's perhaps a bit selfish, but
that's because, in fact, I'm from the government. In the coming months, we will be deploying, from Belgian government, deploying an IPv6 network as a trial. And so first of all, it would be at the agency, but we would like also maybe to enable agencies' employees who would like to try also for IPv6 to, let's say, use a low-cost also end users, routers enabled with v6, which might be interesting because up to now, it seems that there are few low-cost routers which are made, in fact, in Asia and so on, but which may not be imported in Europe due to constraint related to, when I mentioned that, privacy on brevet and so on.
Yeah.
So, first.
It was interesting. Perhaps we will speak about it. But really, at this point, we think we are not ready for distributing on the web, for example.
Thank you.
Okay.
Thank you.
If we can come down, there's two on this side, I'm afraid.
Can perhaps say very quickly that I also got an ASUS access point, which is pretty nice with place for a hard disk inside. That uses the Broadcom chipset like this one, and it's practically the same distribution, so it's pretty nice.
I have a question for Eduardo. You mentioned a better performance with IPv6. I was wondering, is it a better bandwidth, more bandwidth, or lower latency?
It's a question of more bandwidth. If you transfer through a router doing routing, you get more bandwidth. That's on the left is kilobytes per second. It's not written, but it's kilobytes per second. So you really get a big difference.
And about the same slide, do you made some packets per second performance test on the bytes per second?
No, we only measured. To tell you the truth, I cannot remember if we measured it, but I am sure we only analyzed the bandwidth.
Okay, and I have a question for the first presentation about this wireless access system. Do you make any stability test of these different access points, or this test was so short that do you left this access point, for example, a few days and made a constant traffic flow?
Unfortunately, we didn't do it because we ran the access points even sometimes for some hours. But we made one test with the use of D-Link access points. We left them for some days, and we executed iPerf software, and we noticed that in the characteristic or in the graph there were fades. Oh God. There were some fades in the graph during the day, during the working hours. So there was the only long-term test we've done.
Any more questions? It's the gentleman right at the back again.
I would like to say that, for example, for this kind of test, in the two, this router and the other one, we got in every case a doomed router that failed itself about 10 hours or 12 hours. So perhaps it's a matter of a very low-cost router, but we had two good routers and one bad router.
I have a question for Stig. In your presentation, you did advise us to use ULA addresses for configuring our network with V6. This has the advantages like for the NAT addresses we use today, and we know all these advantages. However, one of the nightmares of network administrator today is to manage multiple addresses per host, multiple segments, and so on. So here with V6, one of the main points was that, okay, we will be using one single host address because we have enough to assign them. And which means that for the network administrator, it will have been a nice opportunity to reduce his brain headache. So here, what do we really need to do? Thank you.
Yeah, I agree very much. I don't really myself like the idea of using these ULAs in addition to the other addresses. And I think there's lots of application issues and management issues. So it's sort of just one of the ideas we are sort of exploring. But yeah, I'm not that happy about it.
Because it will be funny playing with IPsec and a lot of applications. They have to use the correct IP address and according to where they have to go.
Yeah. You also have things like applications sending referrals to each other, and you don't know where the addresses might end up. So I might just also say that we are very happy about any feedback. So if you have any experiences doing renumbering, or you are thinking of issues that we haven't thought of, or other ideas, that's very welcome.
So I think we've come to 12:30. Can I say thank you very much to all our speakers today, including the one that came in from the University of Milan. So can we show our appreciation? Lunch is in the marquee and sessions start again at